I'm going to give a demonstration of all of my earlier computer graphics assignments in this video to demonstrate computer graphics and what I've learned from it. Anyways, our first assignment was transforming a cube as it's on the screen. You can scale it bigger, scale it smaller. You can say translate it by the y. I'm lowering the y's value of every vertex of the cube by doing that. I can move it by the x position, and I can also orbit it around the y-axis. Anyways, the way we did this was we used matrix transformations. That's something you would learn in a linear algebra class, but you usually don't get to apply it in a linear algebra class because that's all pen and paper. But how it works is you have a starting position, you multiply by a transformation matrix, and it will output a resulting position when you want to do that transformation. Like in this case, we have a rotation matrix. This is how the cube is sitting still and spinning. And there's other matrices like the translation matrix where I was sliding by x or y. And in our case, we actually have a z value too because we're working in 3 dimensions. So in our case, it's very similar to this, but we just have an extra row and column to the matrix. And yeah, and then there's a scale matrix. I don't see it on this web page, but it's very simple. It's just the diagonals are what you want to multiply by the scaling. So if you want it half as big, the diagonals of the matrix would just be 0.5 all the way through. Anyways, let's go on to the next part. Next part, we learned how to build a camera matrix, which is also more matrix multiplication. The camera has features like its position, the focal length of the lens, which will determine pretty much the field of view of the camera. So it could see like 30-degree angle, or it could be like the human eyes, which see about 180, somewhere close to that. And there will also be I'll open it right here, camera matrix. We have the up vector, which says you can rotate the camera to where it's sideways and so forth, and so up isn't always away from the earth. You have the look at point, it's where the camera is facing, and the center projection, which is basically built up of the focal length. You do all that. Once you build the camera matrix, you can multiply it on the left side of the transformation matrix, and it will give you the new resulting positions, just like we had before. There's a lot more matrices, like the perspective matrix as well, and what's it called? Yeah, and there's one more matrix to get the XY position on the screen rather than in the world. And after that, we ended up implementing lighting of our own. I threw a light in the scene, and the cube turned blue instead of white because its actual material values were that it was a blue cube. On the first one, when we had the spinning cube, it was white because there was no light in the scene, and that's just how OpenGL shows an object when there's no light. And after that, we learned to load models into our scene. This is a very popular model. It's the Stanford Bunny. And what we did is we loaded all the points out of a file into our program, and then we took those points and actually made circles for each point, and we ended up getting this 3-dimensional bunny. We see a little bit of distortion with some of the circles showing up white. That's because it's not programmed to use a Z buffer yet. That's something we did later in the course where we applied a Z buffer, and then that wouldn't happen. A Z buffer basically says to draw the farthest objects first and then draw the closer ones after that. Then you get rid of the fragmenting. We also did the same thing with the dragon. Here's an example of the dragon. And the camera is actually rotating around the dragon. That's why you see the lighting changing while the light is staying in a fixed position. And the way I did this coloring is I colored it different between red, green, and blue based on the angle that the light was bouncing off of the surface. So it'd pretty much say the intensity that the camera receives the light, because if you're facing the surface away from the camera, it's obviously not going to bounce light towards it. And let's see, we eventually got to robots. We used a scene graph to build the robot, where we can walk around and say when I turn the chest piece, it will turn the robot as well. So all the arms, legs, the neck, and the head will all turn right when I turn, and we attached each part to the next part using a scene graph, and I'll explain that right here. The root here in this example is the world. Let's just assume we have a root, a ship, a smokestack on the ship, and some smoke particles. So the root is the world. It has its own transformation matrices to give it its size, its angle, and its position, in case you want to move it somewhere else in the giant 3D world. We throw a ship onto the world, but it also gets all the transformation matrices that the root got, because the ship is within the world. Plus it gets its own ones, which are calculated on this edge that are coming down the tree. So the ship could be elevated onto the ocean and then rotated and scaled, and that all happens on this edge. The same idea with the smokestack. The smokestack is elevated to the and translated to the proper position on the ship. And then the smoke particles are just a translation in the Y value on top of the smokestack. And in order to get the smoke particles' actual position, we calculate the root's position, then the ship's position, then the smokestack's position, then finally the difference for the smoke particles. And the same thing works for every node on the tree. And that's how we end up having the robot able to walk around and not have its limbs detached from the body or anything like that. And eventually we worked on optimization. Here's an example where we surround each object with something called a bounding sphere, and we're only going to calculate the movement of each of the objects and all their animations and everything if those bounding spheres end up somewhere on the screen. It's a lot faster to do that than it is to calculate all the objects and then find out if they're on the screen afterwards, because a sphere is just a point in a radius, whereas an object could be hundreds of vertices, and the computer pretty much wouldn't work if you had too many of those. This is how games work. And I also implemented something to deal with those bounding spheres called frustum cooling. When I press C, the robots speed up, and that's because the frames per second increase to the actual maximum value when I activate the cooling. Don't know. This isn't the final turn-in project, but yeah. Oh, okay, that's why the slides didn't show up. I was demonstrating it in class with a smaller window. But when I activate the cooling, I get the maximum 60 frames per second that you can get out of a general monitor. I turn off the cooling, everything slows down because it's calculating all 10,000 robots in my scene, which is way too much for the computer to handle. And I'll show you an example of that. For the camera, here's a camera. We have a far plane and a near plane. We only want to calculate everything between these, inside this little 3D figure here, between the near plane, the far plane, and the boundaries. And then here's a side view of it. So when I turn on the cooling, we do not calculate this red circle, we do not calculate this red circle, and we do not calculate this rectangle because it's too close to the camera. Everything in between gets rendered by the graphics card. And I guess that's it for this project. On my next one, I will talk about skyboxes, which surrounds the scene with clouds and sky and everything to give you a kind of 3D world. And I'll talk about tessellation, which is turning a surface into a lot of small surfaces so you can reflect the light off of it and look more realistic rather than the rectangle getting one solid color. And I'll talk about my final project where I procedurally generated a terrain, and I could keep resetting it and it would give me a brand new terrain every time, which is really useful for giant 3D worlds because those take too much time to make manually. Alright, thanks.